I'm starting this complicated and beautiful video by filming on my phone. Yeah, that's what you've been waiting so long for. This is the video from the Large Hadron Collider. We finally finished it. So it's important to keep in mind that this video is about a greater immersion in the world of quantum physics. It's a reality that we're living in, and it's like magic. Like magic, that's the tag that you have to keep in mind. To get this topic, you have to watch this video from start to end. You can watch it at school, show it to your parents, and raise the awareness of your friends. I'm sure even the physics teachers will be surprised. Yeah. Hi, all the schoolgoers. It took us 6 months to explain it to you in plain language, so you get it. I want to thank everyone who taught us. First of all, I thank Ivan. He's a scientist from the Large Hadron Collider, straight from the CERN, who helped us dive into it. He took us under his wing and spent hours guiding us. A huge human thanks from me and all the subscribers. The whole Topless project is aimed at videos like this one. Yeah, they're not all that large scale. It's just very difficult. Okay, let's wrap it up. Enjoy watching, and remember, from start to end. July 2012. Hundreds of scientists gathered together to hear a report on the particle that took 20 years, $10 billion, and the construction of a 17-mile underground tunnel to get, and which lasted a yactosecond. That's such a fraction of a second. This old man is Peter Higgs. He's crying because he didn't even dare to hope to live to see this moment. The theory he created 50 years ago proved to be true. The mass of the Higgs boson will determine whether we can find dark matter particles, whether there are other universes, or whether we won't discover anything else in ours. We traveled to Switzerland to dwell on this in detail. We went to the place where the fate of physics was decided, the Large Hadron Collider. It's time to find out what is the code for everything in the world. Will we be able to discover new particles? Is our universe the only universe, or do we live in a multiverse? Why are scientists inventing new physics? How do we photograph the Big Bang? What are the dangers of antimatter? And how to catch something that doesn't exist? Yup. Eon. And this is Switzerland. Such a beauty. This video will be just as beautiful, and I promise you there won't be any formula here except the most important one, E=mc². We've been working on the video for 4 months to talk about the most complicated theories in the world, in plain language. So, here in Switzerland, a particle that was predicted 50 years ago and hunted for the last 20 years was found. It's the Higgs Boson. Everyone must have heard of it, yeah, but just a few, if any, understand what it's for. The Higgs Boson is the final piece in the puzzle of the Standard Model. What is the Standard Model? I came up with a good comparison. The Standard Model is the code of our universe. If binary code is a system of 0 and 1, the code of our universe looks like this. It's a universal code to everything in the world. Everything we know at this point. Everything. People, the air, the water, the sky, the planets, the sun, the heat you feel, the pictures on Instagram, the galaxies, black holes, your dog. It's barking. In fact, all the sounds and smells. And even your idea of turning on this video consists of that. So are we clear now? It's not that complicated, is it? We'll get back to the matter and the Standard Model later. But now, let's start by explaining what the Higgs boson is and what its role is. The most famous formula, E=mc², says that mass and energy are the same thing. That is, in physics terms, I'm 6 quintillion joules, or 70 kilograms. The 69 kilogram and 265 gram of that energy that binds the particles in my body, keeping them from flying apart and falling apart, like in the Avengers. But the other 735 grams are the particles. Strange, isn't it? And that's the mass that the Higgs field gives them with the Higgs boson. The particles move through them and get stuck like a spoon in honey. Think about how hard it is to run in the sand. It feels like you've gained some weight. Likewise, particles get through the Higgs field, thus gaining mass. The more viscous, the greater the mass. The entire universe is permeated by the Higgs field. So no matter where a particle appears, the Higgs field will always indicate its mass. That's how particles know who they are. In other words, without the Higgs field, an electron would doubt that it's an electron. If we could see the Higgs field, we would see people in it like this. And the hand clap is the distortion of the field that is the Higgs boson. That is what the matrix we're living in looks like. The media have called it the God particle. It's tremendously difficult to get in its pure form. It exists in our world for only 1/septillionth of a second. The Large Hadron Collider was built to catch it. And it's right here in Switzerland, right below my feet. The idea is quite simple. It was planned to smash protons and see what would come of it. It all starts with this cylinder, the kind that welders have. It has regular hydrogen, H2, inside, but we aren't interested in it. We need its protons. They're obtained by ionizing the hydrogen atoms, that is, simply splitting off their electrons. Then, they're launched into a linear particle accelerator. Basically, this is a large electromagnet that plays the role of the first stage of a rocket. These particles must necessarily travel there in bunches. This booster accelerates them to 91% of the speed of light. Then, they're accelerated to 99.9% of the speed of light in the synchrotron. Then, the super proton synchrotron accelerates them even faster. And finally, the bunches are released into the main 17-mile-long tunnel. It's almost 4.5 miles longer than the subway line ring. The only difference between the two is that here, instead of trains, beams of protons are accelerated. Here, they accelerate to this much of the speed of light. This is the maximum speed that man has ever been able to achieve. Here we have 17 miles of pipe like this. Such a large number of magnets inside, capable of even accelerating a Boeing 747. Some magnets accelerate the bunches, each time giving them an electromagnetic kick and bending them to make them spin around the ring. The others hold the protons together, preventing them from flying apart. In fact, the whole pipe is a big magnet. The bunches are flying in opposite directions, only to converge at one point and crash, causing the most powerful accident since the Big Bang. I hope you're as curious as I am about what would happen if you stuck your head in there and ran into that beam of energy. Ooh, we know the answer, thanks to one case. This is U-70, the particle accelerator built in the former Soviet Union. More than 40 years ago, Anatoly Bugorsky accidentally stuck his head in there. A high-energy proton beam from a particle accelerator passed through his brain and middle ear and went out his nose. The scientist went deaf in his left ear and began to suffer from epilepsy. But his intelligence hasn't suffered any damage. He's still alive and working at that particle accelerator. Here, in the Large Hadron Collider, there's 200 times as much energy. It'll just blow up your head, and you won't need a hat anymore. Okay, let's not experiment like that. So, we've accelerated the particles, and we've had a very powerful crash. What do we do next? Take pictures. But ordinary cameras won't do the trick. So which ones do then? Like these ones. The central part of the collider is the detector. Basically, there are these huge cameras that record quantum magic. There are 4 main detectors at the collider. Atlas is the longest, a 151-foot-long detector where the Higgs boson was detected. Alice is a detector where the Big Bang is created in miniature. LHCb is aimed at studies that can help to explain the matter-antimatter asymmetry of the universe. We'll talk about it in another video soon. And the CMS, or compact muon solenoid, which, of course, isn't compact at all and weighs like the Eiffel Tower. We are here right now. It's a 5-story Swiss watch, and every part of it clearly serves its function. Pixel and track detectors track the path of particles as they fly out on collision. The colorimeters halt the particles and absorb them to measure energy. Finally, there are huge muon plates on the outside. These are particles that fill everything around us. Here they are, the muon solenoid. It's all needed for the particles flying at the speed of light to put on the most beautiful show, for which we're gathered here. Detectors are not only powerful cameras, but they're also time machines. Alice behind me takes us back 14 billion years, when atoms had not yet formed molecules, and even atoms didn't exist. Thanks to Alice, we know that in the fraction of a second after the Big Bang, there weren't even protons, neutrons, or atoms. Their contents were floating separately, and the universe was fueled by quark-gluon plasma. What else is good about Alice? The temperature reached inside at 9 trillion degrees Celsius. It's incredibly hot. It's 1,000 times hotter than in the center of the sun. That's what happened at the Big Bang 14 billion years ago, and that's what's happening here now. There is no other place in the universe we know of. But this time, protons won't be enough to reach this temperature, so something heavier is needed. Here they slam lead nuclei into each other, the heaviest of the stable elements. If we compare, we can say that at CMS, scientists make passenger cars slam into each other, and here they make heavy tracks slam into each other. That's how they break into millions of pieces. But where do so many particles come from? The point is that something strange happens at the quantum level. Within this energy, new particles appear that weren't there in the first place. Imagine colliding two watermelons and getting oranges, apples, and even feijoa. This is the crux of quantum mechanics. At the same time, it doesn't violate the laws of physics. The mass remains the same. It was 22 pounds of watermelon, and now it's 22 pounds of other fruit. Each time we get a different fruit. So we need to collide many times to get the jackpot. There are millions of such collisions per second. To collect data on millions of collisions, we need a supercomputer, and it's behind this glass. Can you hear that noise? These are all processors that are constantly processing information. This room is huge, about 330 feet this way and 160 feet this way. This place houses an incredible number of processors, so it's very hot inside. 30 years ago, there was only one server here, the server that gave rise to the entire modern internet. This is it. www.html hypertext, that is, the rules by which the internet works today, started here. And this is the world's first network card. YouTube videos, kitty GIFs, government websites, Twitter, Netflix, everything started here, with the desire of physicists to share information about the structure of our world. The collider is called a data miner. They process hundreds of petabytes of information per year. It is such a successful and powerful computational system that it was used to develop a vaccine for the bird flu. This center, along with another one in Budapest, is tier 0 of the computer network. The data from these two centers are sent around the world to be processed by thousands of other scientists. The information from CMS is being studied by 3,800 people here, from ALICE by 1,800 people, from LHCb by 1,300 scientists, and from ATLAS by 3,000 people. Here you can see just one part of the team. They weren't gathered in one place. To continue this video, I need to tell you about the standard model, as I promised at the very beginning. Do you remember what these particles are and what their purpose is? You already know that we're made of cells. Cells of molecules, molecules of atoms, an atom of electron shells, and a small nucleus in the center. A nucleus of protons and neutrons. And this is where school physics ends. But we need to go further, deeper. So, protons and neutrons are made up of quarks glued together by gluons. Those 69 kilograms inside me from the beginning of the video are the gluon springs that glue the 700 grams of my quarks together. They're the elements of the standard model. Nowadays, all matter, absolutely everything, is made up only of these particles. Neutrinos are formed in the sun, but the rest, the bottom, strange, charm quarks, muons, and taus, used to be a matter only at the origin of the universe. They don't exist now, but they can be obtained in colliders. Here are bosons. These particles determine how matters interact with each other. They work like messengers, bouncing between the fermions and telling them what to do with each other. The gluon is responsible for the strong interaction, the most powerful force in nature. It glues quarks within protons and neutrons. The photon mediates the electromagnetic interaction. These are radio waves, visible light of all colors, radiation, and the repulsive force between molecules. W boson and Z boson mediate the weak nuclear force. They're responsible for radioactive decay and thermonuclear reactions, for example in the center of the sun. And here's the particle that bonds everything else together, the Higgs boson. One particle to rule the others. What would it look like? Imagine a ball, like at school. Ready? Forget about it. Fermions, bosons, and other elementary particles can't be imagined, can't be smelled, can't be touched, can't be seen, can't be felt. It's magic, which can be explained only in the language of mathematical equations. Okay, that makes sense, right? Back to the Standard Model. It's not so simple and has a reverse side. Each of these particles has an evil twin. Antimatter particles. They have no difference except for the sign of the charge. The electron has a positively charged electron, known as the positron. The proton has an antiproton, and hydrogen has an antihydrogen. When colliding with the matter, they mutually annihilate, releasing energy. Antimatter can be found in space, or produced here in the antimatter factory. It's the most expensive substance ever known to humankind. Antiprotons fly in here at almost the speed of light, really fast. But it's impossible to research them all at once. It's like spotting a train number at full speed. Impossible. Hence, the antiprotons must be decelerated. It's done here, in these decelerators. Every time the proton flies through them, it loses energy, and eventually slows down 1,000 times, until it finally gets into a magnetic trap where it can be stored for years. Here, powerful magnets repel antimatter particles from the walls. It's like the ghost trap in the Ghostbusters movie. It prevents antimatter from interacting with ordinary matter. Yeah, antimatter is dangerous in large quantities. 2 pounds of antimatter coupled with matter can make an explosion with the power of 1,000 atomic bombs dropped on Hiroshima. It would be an absolutely pure explosion. No radiation, no waste, just an explosion. For antihumans, who would be made of antimatter, we would be antihumans. That's why Richard Feynman once said, if you hold out your right hand to a man, and he holds out the left one, run away. Because you might explode. Well, I realize that it sounds just like a new season of Rick and Morty. An absurd, confusing reality, but that's the reality. The quantum reality in which we live. The Higgs boson is the last piece of the puzzle called the Standard Model. Its mass answers the question, is there anything left to be discovered beyond this table? And most importantly, what universe are we living in? If it turns out to be light, 115 GeV, then the supersymmetry theory, or SUSY as scientists call it, is true. Supersymmetry is not the usual right-left symmetry. Supersymmetry is the symmetry of matter and interaction. In the supersymmetric world, everything is once again turned upside down. Each particle of the Standard Model gets a supersymmetric partner. Photino for photon, squark for quark, Higgsino for Higgs boson, and so on. Their functions change completely. In our casual world, fermions are bricks and bosons are builders arranging them, while in the supersymmetric world, and vice versa, bricks would arrange builders. Supersymmetry is a cherished dream. But why? It might solve a huge iceberg of problems. One of them is this. Why are some particles in the Standard Model billions of times heavier than others? It's like comparing the mass of a mosquito and a Boeing 747. That's how great the difference is. Supersymmetry solves this problem. But if the Higgs boson is heavier than 140 GeV, then another theory is true. It says that our world is not unique, and we live in a multiverse. That is, there are many universes, and anything can happen in each one. Multiverse sounds cool, yeah? Here's what Stephen Hawking said about it. Somewhere out there, Hillary Clinton is president, and I'm the world record holder in the marathon. Great! Huh? But for scientists, it's a defeat. Since, They've spent hundreds of years trying to learn the universal laws of nature and find the answers to all the questions. Who are we? What are we made of? And where do we live? But if there are many universes, then we live in a random world of 10 to the power of 10 to the power of 10 to the power of 7 others? That's a lot, and the Big Bang Theory is just a puff in a world of other puffs. So which of the two theories is true? What kind of world do we live in? It was defined here, on the 4th of July 2012. It was the most important event for elementary particle physics, the discovery of the Higgs boson and the announcement of its mass. Physicists queued throughout the night, just like for a new iPhone. The answer to the question of what universe we live in depends on one thing. How much does the Higgs boson weigh? And does it even exist? Finally, at 9 a.m. local time, the conference began. Scientists spent a long time showing each other charts, diagrams, and bright drawings that made my eyes water. But the most interesting were these charts. One axis shows the number of events, and the other shows their energy. The curves are straight, except for one place, 125 GeV. So, the particles are there. Higgs boson, the one sought by scientists. The chance that they were wrong? 1 in 3.5 million. While everyone was shaking hands, a man was crying right in this seat. This elderly man is Peter Higgs. He's crying because he never expected to experience this moment. The theory he created 50 years ago turned out to be true. A year later, he received the Nobel Prize in Physics. The most significant physics event of the 21st century has left scientists puzzled. 125 GeV? Really? We were expecting heads or tails, but the coin fell off the edge. That is, the result is in the middle. The weight of the Higgs boson is 125 GeV. If there is a God, creator, whatever, then he carefully hides the truth from us, leaving only clues. He seems to play hide and seek with us at the point when we're about to get close to the truth. He adds another challenge, as if saying, "Wow, guys, you're good, but not this time." We are the same Homo sapiens as 100,000 years ago. The same brain size, and the same physical capabilities. What makes us different is the time we live in and the culture. That's it. Whereas, science used to progress in small steps, and now it's moving at the speed of a truck. But perhaps, quite soon we'll hit a wall, and won't be discovering any new particles. Maybe we've reached the great desert of physics, where we can't discover anything else, and that's the limit. There are no other particles. Even if we build a huge accelerator around the black hole in the center of our galaxy, we won't discover anything new. While skeptics were writing their articles, CERN was working on an upgrade of the Large Hadron Collider. It's begun accelerating and smashing particles in 2021. Now, it works at higher energies and with more accurate detectors, the data from which is processed by artificial intelligence. This means that we're back in pursuit of answers of the most important questions in the universe. Anticipating the skeptics in the comments, I want to answer the question, how can the Higgs boson be useful to humankind right away? I'll quote Frederick Bordry's thoughts on the subject. There is an electron, and there is electronics. People knew what electronics were, but they didn't know about the electron. Now, we have boson, and soon, there may be bosonics. So far, our minds are incapable of figuring out how to use the Higgs field to our advantage. But sooner or later, we'll figure it out. Maybe we can learn how to disable mass, and then any matter will behave as it did after the Thanos snap in the Avengers. Look, he disabled the mass of Spider-Man's quarks. This could be used as a weapon. For example, to stop a comet flying toward the Earth by turning off the Higgs field for it. Its gluon bonds won't be able to hold the particles, and it will disintegrate. That's all there was to tell. So, I did. One more thing. Everything that's happening here at CERN is done for the first time. These machines have neither commercial nor military potential. Considering the economic value, it's a waste of money. But for scientists, the collider is priceless. After all, it helps answer the most childish questions. Who are we? What is the world made of? How did it begin? And how will it end? And, as always, pump up your brain. Bye.